Imagine teaching an AI to navigate the real world. You don't show it one path. You give it thousands of simulated scenarios. But building those simulations by hand is slow, and once the AI masters them, training stalls. That's where world models come in. They generate dynamic environments, so agents can practice endlessly. But most are built on standard autoregressive language models, which generate text left to right, one token at a time. This creates a critical flaw. They're prefix consistent but globally incoherent. They lock into early predictions and can't look ahead or backward to verify the whole simulation. For training agents, this means contradictory states, brittle policies, and severe overfitting. Researchers recently tested a different architecture, masked diffusion language models. Instead of guessing word by word, MDLMs start with a partially masked state and iteratively denoise it bidirectionally. They evaluate known tokens, upcoming context, and everything in between simultaneously. This enforces global consistency across tool responses and environmental transitions. When trained on nearly 240,000 environment trajectories across software, customer service, and research tasks, MDLMs outperformed larger autoregressive baselines. Even more importantly, when plugged into reinforcement learning frameworks, agents trained on MDLM rollouts saw absolute success rate improvements of up to 47% on completely unseen environments. But architecture alone isn't enough. When researchers trained these agents using group relative policy optimization, the world model exposed systematic failure modes. Pagination duplication caused double counting. Hallucinations invented non-existent objects. Messy JSON corrupted conversation history. State tracking failed when identifiers were dropped or repeated. And verbose drift broke deterministic grounding. The fix wasn't more data, it was rigid guardrails. Stricter prompt constraints, deterministic responders for critical actions, and cleaning the data pipeline to unwrap malformed JSON before training. Teaching an AI to simulate reality isn't just about scaling models. It's about aligning architecture with structural integrity, anticipating failure modes, and enforcing strict state consistency. As mass diffusion scales, we're moving toward agents that don't just memorize paths, but truly understand dynamic environments.